Welcome back. This is a video recording for Cosmology class on October 1st. As I said, this one will be delivered as a video recording. I remind you that we, for the first time, discussed the Friedman equation. And I mentioned that the correct, and I say correct, it's the fully general relativistic Friedman equation now. We have this usual term. And from now on, we would like to use energy density as opposed to mass density. So we have extra speed of light square. And then finally, we have energy density, epsilon, which may be a function of time. And for the integration constant term that was appeared in a Newtonian Friedman equation, we replace that with the curvature. And we now also have the radius of the curvature square and scale factor square. So I'd like to have, let's see if I could make it correct. So this is one of the most important equations that we discussed during this semester, which we call now Friedman equation for general relativity case. Now, let us remind ourselves about Einstein's famous energy mass formula. I assume we know this from classical mechanics at least. So general expression for the energy of a massive particle contains the usual term mc squared. So let's square it for the moment. M squared c power of 4 plus and kinetic energy term. And if you express that in terms of momentum, you'll have p squared c squared, and whole thing has to be squared. So that's Einstein's energy mass formula in special theory of relativity. And we discussed some time ago expansion of universe. That is related with the scale factor change as a function of time. And except this expansion itself, so you can also think about the motion of a particle. I make a quote unquote. So this motion has nothing, this particular one is nothing to do with the expansion. That's independent of expansion. We call this motion as peculiar motion. So this is the motion of the particle even the universe is static. So we want to re-express this when this peculiar motion is significantly smaller than the speed of light. Then the linear momentum is running out of power for the pencil. Let's see how far we can go. MC. We usually have gamma factor, but for non-relativistic limit, that's what we can do. We can factor out mc square from the square root. So we have 1 plus, we will have p square. I'm gonna have m square. I already have c square, so the only thing I have c square, and whole thing is 1 over 2. That is mc square 1 plus. This is nothing but v square over c square 1/2. And if I expanded this, I'm going to have mc square plus the usual classical kinetic energy term. So that's what you expect for a non-relativistic massive particle. So let's write that down to be non-relativistic. When I say massive, it doesn't really mean that it's heavy. It means that m is not equal to 0. Neutrino is also finite mass, but it's more or less relativistic. And you can also think about, on the other end, photons. And they are quite different. According to Einstein's theory, so photon energy is fully relativistic because it flies at the speed of light. So hf is the momentum times speed of light. So if you compare this type of expression and the expression for fully relativistic massless particle, which is photon, they're quite different. And we will come back to this point later on. And the constant term, if this is less than 0, then we say that the kappa should be +1 because of the extra minus term, which is, try to remind you, this negative term. And because of that, when u is greater than 0, that means negatively curved space. And of course, if u is 0, then it means it's flat space. Now we can define, well, we already sort of did, ht is equal to a dot at any given time divided by the scale factor at any given time. So Friedman equation becomes h, undo, zoom it again, h t square is 8 pi g or 3c square epsilon t minus the curvature term and scale factor square the denominator. That's another form. Now if you evaluate this differential equation, as of today, we have, so at t is equal to t0, I have h0, which is a number, 8 pi g over 3c squared. And let's call that to be energy density of everything now, today. And then kappa c squared over r0 squared, and scale factors of today is set to be 1. So this is the relation that we right now have. So this, I emphasize you that this is not the differential equation anymore. This is just a relation among H0, energy density 0, and so on. So suppose for flat space, so if we have simpler form, h squared t has only one term, 8 pi g, 3c squared, energy density. So we reverse this, epsilon t is 3c squared over 8 pi g h0 squared. In general, this is not satisfied, but if the space is flat, then we have this relation. So for the general case, when in any case you can define this quantity regardless of the space is flat, curved, positively or negatively curved, you want to define this quantity as a particular parameter, which is a function of time. We want to call this to be critical density. Critical. That's just the definition. All right. And by having it, let's go to black color and removing ht from Friedman equation, what we can do is, because we know epsilon, we have this relationship as well as this relationship. We can remove h in such a way that 8 pi g over 3c squared epsilon minus epsilon critical kappa c square over r0 square a square. And mathematically everything is equivalent to each other. We are just defining another variable to rewrite the Friedman equation. But if you do so, now we can discuss something. If energy density is greater than this so-called critical density, then we say that kappa should be +1 because left-hand side is positive, so kappa, there's only one thing you can do is kappa is +1. If otherwise, if opposite, then it's negatively curved. so that kappa should be -1. And in fact, we can numerically calculate critical density as of today, because we only know Hubble expansion rate as of today numerically. Speed of light, gravitational constants are given. H0 is about 70 kilometer per second per megaparsec. So if you plug this in, this is approximately 4870 MeV per cubic meter. So if you think about the mass of proton being slightly less than 1 GeV, 1000 MeV, this is about 5 protons per cubic meter. It looks like fairly small, but if you express it in terms of mass value of the sun per megaparsec cubic, then the numerical value that you're gonna have is huge, 10 to the 11. And there's some numerical value of 1.28 and so on. So depending on which unit you are writing, you can say, well, there's only 5 protons per cubic meter, or it should be 10 to the 11 solar mass per megaparsec cubic. So one has to be a little careful how to represent in numbers, and sometimes you want to compare with the numbers that we are familiar with, such as protons per cubic meter, or if you express this energy density in terms of astronomical scale, like solar mass per cubic megaparsec, then it's a different story. And let's further play with the Friedmann equation. So let's define capital omega, which is the ratio of energy density of everything divided by the critical density. And by definition, we don't know what the value of this is. It's not constrained. And you can measure this. How do we measure? We'll talk about it much later. So let's take a look at the numbers. Measurement lies on, we only can measure this as of today because we live in today only. It's fairly close to 1. So it's bounded from 0.995 and 1.005. So less than 1% of the uncertainty, if you want to say. If you divide Friedmann equation by h square itself, then what you want to get is 1 minus omega t is minus kappa c square. It's just another expression that you can derive very easily. R0 square, scale factor square, and since we divided by Hubble's expansion rate square, that's what you get. Now, one thing to note is right hand side contains kappa c square, r0 square, a scale factor square, and h square. This we say that this is cannot, right hand side cannot change sign. Because everything is constant square and there's only one parameter that may change the sign, which is kappa. Assuming kappa is a constant, it could be +1 or 0 or -1, but it doesn't change over time. Well, you can still think about it, but we normally assume the characteristic of our space is a constant. So fancy way of saying it is not kappa is not a dynamic quantity. There are crazy theories that allows kappa to be a function of time, but let's don't consider that, at least in this semester. So if, for that reason, if omega is less than 1, and it has to be like that, for all time, forever. And similar for omega being equal to 1 or omega being greater than 1. And at present, we have 1 minus omega 0 is minus kappa c square r0 square h 0 square. So you can rewrite in terms of kappa r0 square, and then you have h0 square over c square, and then because of negative sign you flip the order, omega 0 minus 1. So from this, if you know, knowing omega 0 will give us sine of kappa. And if you know h0, then you can get the radius of the curvature. And I will not discuss in this my lecture, but the problem is there are many, at least 2 independent ways to measure the Hubble expansion rate as of today, but we have a problem. 2 independent measurements are not agree each other. So that's called Hubble extension. So there's some issue of the value of radius of the curvature for the moment. I remind you one fact that we discussed some time ago. The Friedmann equation itself, they contain both scale factor and time derivative of the scale factor and energy density. So because of that, it cannot be solved by itself. You need more information to solve it. So that's the subject of next part. So I'm gonna have new page. And we want to discuss a new two equations. And the first one is called fluid. And the second one is acceleration. Equations. To discuss this, let's again consider the first law of thermodynamics. We did this some time ago, and the statement total heat change of the system is in general change of the internal energy and the change of the work done by the ideal gas. And since our system is the entire universe, there's no heat coming in, there's no heat coming out. Everything is in our universe. So we say this is, or sometimes it's called adiabatic. Process. This term was already appeared in your freshman physics. So this is 0, and we divide everything by infinitesimal change of time. So we are saying that E time derivative plus P V time derivative is 0. Now let's work on with a scale factor. So I have volume is the volume 4 pi over 3 RS3 and scale factor power of 3. And if I make a time derivative and constants are there, and it's a 3a square and a dot, and I can multiply a and a to make it equal. Then I have a power of 3, and with that I recover volume, but factor 3 and a dot, a has to be taken out. For the internal energy and internal energy density times the volume. So if we are interested in time derivative, the energy has two pieces. One is change of energy density, or the change of the volume. And change of the volume that we already discussed. So V comes out, and I have epsilon dot from the first one, and from here we have 3 a dot over a and energy density itself. So now it's time to combine everything. What do I mean? I mean we plug everything in here. So from E dot, we have two terms, and we have P V dot. And V dot is already known as this. So we can take out V from all the three terms. And we have epsilon dot plus 3 A dot A epsilon. And the final one, we have 3 A dot over A, and we have P. So the last term is P. Pressure is 0. And has to be satisfied for every volume and any values of pressure, scale factor, time derivative of scale factor, and so on. So we conclude that 3A dot A, whatever we have in the parenthesis, we can have E plus P should be 0. And we call this to be fluid equation. So we assume the first law of the thermodynamics into our universe and derive one differential equation, which we call fluid equation. Let me write down the Friedman equation once again. Now I want to multiply by a square so that I have a dot square only on the left hand side. And I have epsilon and a square and kappa c square r0 square, and a square in the denominator was cancelled. Let's take a time derivative. So I'm going to have 2a dot a double dot is equal to 8 pi g over 3c square. And then I'm going to have e dot a square plus, now derivative goes to a, so I have factor 2 epsilon a dot. And this curvature term is a constant, so it doesn't contribute. So by dividing everything by 2a dot a, I'm gonna have a double dot divided by a. So that's 2a dot a being divided. So 8 becomes 4 pi g 3c square. I have epsilon dot. A square becomes a, and I have a dot in the denominator. I have factor 2, so I have 2 and epsilon. And from fluid equation, you can change this to E dot and multiply A over A dot and express in terms of everything else. That's first of all, we have negative sign, and we have factor 3 and E plus P. And let's have this to here. Then we have a double dot a is equal to 4 pi g over 3c square. And we have minus, so minus 3e minus 3 pressure, 3p. So that will allows us to take out minus and e plus 3p. We have minus 3e, and there's also plus 2e, so overall result is only e, minus e. So now our finding is, suppose this epsilon plus 3p positive, and because of the negative sign, we say that acceleration has to be negative. So it's a negative acceleration. And we sort of tend to think the energy density, well, this has to be positive. So if pressure is less than minus 1 over 3e, in this case, now acceleration becomes positive because this is positive. Then what does it mean? Well, this means negative pressure. And first of all, you may consider, hey, what's negative pressure? Because the pressure that we discussed in freshman physics was all positive. One example you can think about is, suppose you stretch out rubber band instead of pressing it, and inside of the rubber band it will be stretched out, so it will feel negative pressure. So that's one example. But if you think about normal quantity, what corresponds to the negative energy? And it will be related with this negative pressure is something called dark energy that we will discuss sometime later. Okay, let's see how are we doing. I'd like to finish right here for today's lecture, because equation of state and learning to love lambda is like to reserve for next video. Okay, so let me stop here and enjoy your holidays and wonderful food, and I'll see you on next video. Bye bye.